Very much. Maintenant, donc on va parler d'applications dans le domaine du médical à travers une autre aventure entrepreneuriale étonnante et en plein développement qui s'appelle Tissium. On va parler avec vous, Maria Pereira. Thank you very much for being here. And to explain to us what's the story of this company and what at the beginning was what was the idea of the bio-inspiration. It's a very strategic innovation, quite disruptive in to avoid suture. So thank you very much for being here and to speak to us about Tissium. The stage is yours. I don't know if you want to stay there or to go where you want. Thank you.
Okay. Bonjour. Bonjour tout le monde. Merci beaucoup. Thank you very much for having me here today, and thank you very much for the invitation. Unfortunately, I'll have to do this presentation in English. Perhaps next year I'll do it in French.
Oh, just what Tissium, is it a French company?
Yeah, it's a French company. So we are based in Paris. So it's a technology with an origin at Massachusetts Institute of Technology at MIT in the US. That was fully licensed by Tissium. We used to be called Gecko Biomedical. Core operations are in Paris. We have our manufacturing facilities in the north of France, close to Lille, and we have currently also a small office in Boston, but the majority is all in France. So, and I will tell you the story of Tissium, and I will start this story even before Tissium existed. Because for me, the technology, the story of Tissium starts with this email. So back in 2009, I was a student at MIT in the laboratory of Professor Jeff Karp. And one day, I was starting my studies, and one day he got this email from Dr. Pedro Del Niro, which was the chief of cardiac surgery at the Boston Children's Hospital. So basically, his email basically said, are you willing to help us develop new technologies to close ventricular septal defects? So ventricular septal defects are small holes between the chambers of the heart that are quite common in newborns. And they need to be closed to allow normal blood circulation. When discussing with him, there was a lot of brainstorming. So what were the challenges to close these defects inside the heart? And basically, what we realized is that the way it's currently done. So there's two main technologies or two main strategies to close these holes between the chambers of the heart, which are to do an open chest procedure, go inside the heart, suture, and close back. And if you imagine that this is being done in newborns, it's a highly invasive procedure. And another strategy that can be used is to basically use what is called implanter devices, which are basically metallic devices that can be delivered minimally invasive inside the heart. But basically, the way they attach to the tissue and they remain attached on the tissue is by mechanical compression. So basically, these are metallic devices that have shape memory properties. They compress the walls of the heart, and that's how they remain attached, and that's how they can close these defects. The key challenge is that we are talking about metal inside a baby's heart, and metal cannot biodegrade. So as the child is growing, very often these devices need to be taken out, and a new device needs to be placed in, simply because the device cannot grow with the child. So having this problem, the key question for us is, if you have a hole inside the heart, why not simply using a glue? The problem is that when we started to look to the market and try to understand which glues were available for medical use, what we realized is that currently there's two main types of glues. Some that basically are very biocompatible, but they don't adhere very well to the tissue. So if you think we are inside the heart, very dynamic tissue, a turbulence of blood inside the heart, definitely something that doesn't adhere strongly to the tissue will not work. And the second type of materials that exist, basically there are some materials that can adhere strongly to the tissue, but they have two core issues. The first one, they can be quite toxic to the tissue. And the second main issue is that they are very reactive. So as soon as you deliver the material inside the heart and it contacts blood, it will start to polymerize. So the surgeon will have no control, the material will be washed out, and so the surgeon will have no control on where to position the adhesive and how to activate it inside the heart. So we started to basically to brainstorm if we wanted to develop something to solve this problem, what would be the core characteristics that the material should have. So first we wanted something that would work, could be delivered minimally invasive inside the heart where the blood is flowing. So we wanted to have something that could be resistant to washout. So something that will not simply go away. And we also wanted to have something that the surgeon could control when to position and when to activate adhesion. So we wanted also to have something on demand. So something that the surgeon could control, position and activate. And of course, we wanted something that also could be compatible with a medical use, something that was biocompatible, something that was biodegradable. And also, we started to think that we also wanted something that was programmable, right? Because we always saw heart is a first application, but if you can get something, if you can design something that adheres very well to the tissue, that is friendly, and that is quite compatible with the minimally invasive surgery, for sure there will be other applications for us to explore. And so, to solve this problem and having these key criteria, I think one of the things that we did was to look to nature, really try to understand what are the creatures out there that have been able to already solve this problem of underwater adhesion. So our core inspiration was to look to, it was not to mimic exactly the specific chemistry of these creatures, but it was to get inspiration on how they work. So one of the things that we realized is that to be able to adhere in challenging environments, in very wet and dynamic conditions, several creatures have developed specific technologies or techniques, specific materials that can achieve this. For example, if you look to snails or sandcastle worms, they basically secrete very viscous and hydrophobic materials. Because they are hydrophobic, they cannot be washed away, and also because they are viscous, they will not go away. They will not go away from the targeted location. So we took inspiration from these macroscopic properties and tried to design something that could be compatible with the medical use. And that's how we came with our core technology. So basically, and let's see if the video works. Yes. So basically, we developed a new polymer that is viscous and hydrophobic, similar to the secretions of snails and sandcastles. So it cannot be, you can spread it on the tissue, you can spread it on the surface, even under water conditions, and it will not go away. So basically, it remains exactly where the clinician wants to apply it. Second, the material, to make sure the surgeon could control when to activate it. So basically what we did is that this material only adheres to tissue once it's exposed to light. So light allows us to control exactly when to activate. So the surgeon can go inside the body, he can position the material where he wants, and then only use light to activate the material. Also, once it's polymerized, once it has been light activated, the material is elastic, so it can comply with the dynamics of a beating heart, basically. It's biocompatible, and it biodegrades slowly over time. And the biodegradation is important because it avoids the need of a second surgery, for example, to go inside and to change the material when the tissue changes or grows. So, and I think once we did the proof of concept of this work, so at the time still at MIT, and then basically we met two outstanding French entrepreneurs that saw the technology and came with this broad question. So what if could we simply use this to replace sutures? And that's how Tissium was born. So if we look to how surgery is done, I think it's quite incredible that technology has evolved so poorly over the last, I cannot even say centuries, over the last millennials. Suturing has been always a technique used for surgery to close defects. I think the core challenges are that basically every time you apply a suture, you are creating a defect. You are creating damage to the tissue. And if you think about very sensitive tissues, for example, vascular tissue, nerves, and so on. These sutures can have negative impact on the long term. So that was our core mission. Basically, we started in 2013. So the company was founded in 2013, really with this mission to bring a new technology that could help reconstruct and repair tissues, namely through the replacement of sutures in surgery. So the way we are making our technology evolve, if we think, we are a small company, and we have a big mission to replace sutures. There's different procedures where the technology can be applied, different surgical scenarios. So the way we develop our technology and we make it evolve, it's a little bit as nature, right? We don't try to go from scratch all the time. We basically adapt the key components and make them evolve to target specific clinical needs. So for us, our technology is the combination of three key components, so the polymer that we developed, basically our adhesive, the light to activate this adhesive, and also how to deliver this adhesive inside the body. And it's by playing through a modular approach on these three key components that we basically can design different solutions. So as I said, the polymer is our key component. So basically our polymer is composed of three core, let's say, monomers. And basically, by changing the ratio of these monomers, we can mimic the properties of very different tissues. We can achieve materials that are more soft, or achieve materials that are more stiff, to basically be able to match the properties of different underlying tissues. Because if you want to glue inside the heart, or if you want to glue, for example, a bone, the properties that you require are quite different. So we can play with the chemistry of our materials to be able to achieve a broad range of properties to basically match the clinical needs. Then, as I said, the second core component of our technology is how to deliver our material inside the body. So depending on if you want to coat a surface, you may want to spray the material. If you want to deliver the material in a very specific location, you can use for example, a very small spreader that can deploy the material even under water conditions. Or if you want to deliver it in a minimally invasive procedure, you can leverage, for example, laparoscopic tools that can, through very small holes in your body, they can deliver the material inside, and then the material can be activated. So we have to basically to make it work, as I normally like to say, it's not only about the material, it's also how you make it easy for the surgeons to use it, and how do you make it adaptable for different surgical procedures. And of course, then we have the light component. And it's basically by playing with these three variations, we are able to deliver different technologies. So our first technology that we have developed over the last years, it's a vascular sealant. So we got CE mark for this technology back in 2017, and we are currently, for example, working on a second program on peripheral nerve that we expect to bring to the clinics quite soon. And so the way we are developing not the technology, but as the company, is really to create an integrated ecosystem that goes from early stage research, really understanding the problems that we are solving, making sure we master the manufacturing of our materials, and then also deploy them to our customers. So basically bring them to the market. And basically, as I said, one of the things that we have done to make sure we mastered this ecosystem was to build our own manufacturing facility. So currently this is based in the north of France, in Lille. And so basically out of this factory, these polymers, are being produced in this manufacturing facility, and really to be able to supply to partners, to customers, to the hospitals, and so on. And so I think more on a personal note, I think for what we are really trying to do on the company is create this innovation ecosystem. And for me, innovation is not only about the core technology, but also how you basically develop the company, how you bring your products to the market. And so there's different components that need to be taken in consideration, especially because we are talking about a medical technology. So key things that are very important, of course, is all the quality of your products, and making sure that you have something that is safe for the patient. And so I think looking back, I think my big lesson learned is that to basically bring these innovations to the market, to bring something really new to the market, it's sometimes, of course, creativity is important and getting the right sources of inspiration is important, but also being disciplined to really understand what is the need that you are trying to solve and making sure that you design to that need. And of course, nature is always a great source of inspiration to be able to have that discipline and to make sure you design something that is meaningful and can address the problem that you're looking to solve. Thank you.
Thank you very much. Thank you very much, Maria. Just one or two questions. Si vous avez des questions dans la salle, allez-y. At the beginning, it started with some kind of a challenge, a question. Who is there to try to work together to solve this problem? So who had the idea to look into nature to find the answer? And in terms of methodology, because here we have the demonstration of things are done today, so it's easy to understand. It's so easy. But at the beginning, who had the idea to look into nature if there is any answer? And how did you get the right answer?
Yeah, so my advisor, so Professor Jeff Karp, at the time he had been working on other adhesives for medical applications, and at the time the core technology he was interested on was gecko adhesion, and basically leveraging understanding how geckos use their very nice topography on their pads to be able to attach to different surfaces. So he had published some work on that. And initially I was supposed to work on that technology, but once we came up with this problem, we very quickly realized that that was not going to be the technology that was going to be used, because there was very dynamic environment, very bloody, very wet. So and we needed to make sure that the surgeon could control the technology. So that's how we started to look. Let's not only stick to geckos, but let's look a little bit to the size. There's been other creatures that have been able to solve this problem, right? So I think that's always important to keep some mental flexibility to understand exactly what you are trying to solve and design exactly for that. And then there's always nature to be that source of inspiration. And nature has been able to solve these problems not sometimes in a single way, but on multiple ways. So I think that flexibility is always very important.
Okay. And are you, as Guillaume said, I don't know if you get the point, but he is actually surprised by other applications from their innovation. Are you sometimes?
Yeah. So we do work a lot with, especially with clinicians, trying to understand where in the body it can be applied. And we have very different requests for the more varied applications, from the nervous system to the heart and different applications. So it's always very interesting to think through the breadth of uses where it can be applied. So for now in the company, we have also some requests outside the medical space. I think for a question of focus for the company, we have decided to stick to added value applications on the medical space. But we always get also requests outside that space. But for now, we cannot take them on, but perhaps in the future.
Okay. Thank you very much, Maria. Pereira, Tissium. Pardon. Une entreprise à suivre. Merci beaucoup pour ce témoignage. Les stratégies d'adhésion dans le vivant sont captivantes. Effectivement, elles sont extrêmement variées. Du côté de vos collègues américains, François, au centre de recherche de la NASA, il n'y a pas très longtemps, là, il y a à peu près 6 mois, ils ont sorti ce qu'ils appellent le Gecko Gripper. Ils ont réussi à reproduire l'effet Van der Waals de l'adhésion de la patte de gecko, qui n'est pas une glu, là, pour le coup. Il n'y a pas de colle, il n'y a pas de ventouse. Il a sur chacun de ses doigts, de chacune de ses pattes, des milliers de poils. Ils ne sont pas sensoriels comme les poils de grillon de tout à l'heure, mais chacun de ces poils se subdivise en une centaine de spatules, et donc vous arrivez à un niveau atomique qui crée un effet dit Van der Waals d'adhésion. Et ils ont fait la démonstration de ça il n'y a pas très longtemps. Comment vous travaillez avec vos collègues américains sur ce type d'innovation? Vous êtes concurrents ou il y a des échanges?
Alors, avant de vous répondre, et je vais répondre, peut-être juste une remarque sur ce très bel exemple que vous donnez, et aussi pour faire suite à la présentation, la notion de colle. Je l'ai dit tout à l'heure dans mes propos liminaires. On a beaucoup de défis, beaucoup de challenges quand on veut faire des satellites, des fusées, des missions habitées, etc. Et un des défis que nous avons, c'est de réduire la masse au lancement. plus vous envoyez de kilos, plus c'est compliqué, c'est cher, il y a des problèmes, il y a des challenges, etc. Donc, coller, truc tout bête de la nature, comme le font les geckos par exemple, des colles, c'est pas cher, c'est souvent très efficace, très solide, et bien sûr, ça réduit significativement la masse. Donc, ce n'est pas pour rien, pour revenir à votre question, ce n'est pas pour rien que la NASA, mais aussi nous en Europe, on regarde ce genre de processus. Lorsque on se place, on vous l'avait dit en introduction, je suis responsable de la prospective au CNES, lorsqu'on réfléchit en termes prospectifs, c'est-à-dire à moyen long terme, dans 20, 30, 40, 50 ans, il y aura des habitats sur la Lune, des habitats sur Mars, des grandes stations orbitales. La question de l'adhésion entre éléments, non pas terrestres, mais ailleurs, sera une question fondamentale. Il faudra coller, mais il faudra aussi être résistant, je l'ai dit tout à l'heure, résistant aux agressions hostiles, aux milieux hostiles extérieurs. Et donc, toutes ces problématiques, la NASA les regarde, nous on les regarde. Et pour répondre directement à votre question, oui, bien sûr, on travaille avec la NASA sur tous les sujets du spatial, en particulier sur celui-là, et on travaille aussi avec d'autres agences spatiales dans le monde.
Ok, merci beaucoup pour ce complément. J'en fais un autre sur ces stratégies d'adhésion avec une autre valeur ajoutée. C'est par exemple le groupe Ford qui est en train de travailler sur cet effet gecko après avoir collaboré pendant 2-3 ans avec nos confrères ou collègues américains du Biomimexpo 3.8, justement pour essayer de mieux désassembler les matières assemblées dans l'habitacle automobile pour améliorer la valorisation des produits en fin de vie du produit et donc dans une stratégie d'économie circulaire. Les matériaux de différentes natures qu'ils assemblaient et qu'ils continuent à assembler dans les habitacles, du textile, du bois, du plastique, etc., sont pour le coup là souvent bien collés. Mais ce qui est génial dans le gecko, c'est qu'il colle et qu'il se décolle. Et donc Ford s'intéresse à ça pour pouvoir décoller, désassembler facilement les différentes matières assemblées dans l'habitacle, parce que plus vous les désassemblez facilement, plus vous pouvez les valoriser en fin de vie du produit, en tri sélectif et en économie circulaire. Donc là aussi, problem solving industriel, réponse bio-inspirée. Merci beaucoup once again Maria Pereira.